So when you talk about the inverse function, basically, now, firstly, notation. F of x is your original function. F inverse x, when you show, it is shown by like this. So F inverse x, when you have, it is f to the power minus 1x. The general confusion is that this is also equals to 1 upon fx. That's not correct. This is referred as a reciprocal function, and this is inverse. Both of them are quite different. So this is inverse function, and this is called as reciprocal. So they are not the same. Please remember that. Um, so yeah. Now, what's the general logic? Like, how do we define inverse function? Now, actually, inverse function is a mapping. Like, for example, if we had like 1, 2, 3, 4, and we map with like 4, 5, 6, 7. Let's say one was mapped with 4, 2 was mapped with 5, 3 was mapped with 6, 4 was mapped with 7. Then what happened is that this is the original function mapping. This is one-on-one mapping. And when you talk about inverse functions, in inverse function, the mapping will be 4, 5, 6, 7 with 1, 2, 3, and 4. So 4 will be mapped against 1, 5 will be mapped against 2, 6 will be mapped against 3, and 7 will be mapped against 4. So what actually happens is that if I have a point x comma y on the function graph, the same point becomes y comma x on inverse function. So you can understand already the properties of x and y is getting interchanged. Now, the algorithm is that when you talk about inverse function, suppose there's a function which we got as, let's say, 2x plus 3. And now I want to find out the inverse of this function. So the simple algorithm is that you interchange x with y, and then make y the subject of the formula. The subject of the formula. So now, for example, if I have, let's say, uh, y is equals to 2x plus 3. As you know, f of x is nothing but the y. So y is 2x plus 3. So interchange x with y will be 2y plus 3. So when you solve for y, 2y is nothing but x minus 3. So y is x minus 3 over 2. So this part that you get is the inverse function. Now, when you look at the graphical representation of these two, so now, for example, if this is my y-axis, this is x-axis. Now, what I want to do is, I just want to draw the, let's say, where is my original function? So 2x plus 3 is going to be cutting like something like this here. So that is, this cuts at 0, comma 3, and this cuts at, this will be negative 3 by 2, uh, comma 0. And now when you draw the inverse function, okay, so if I just draw the, let's say this is y equals to x line. When I'm drawing a y equals to x line, that's something like here. Now when you draw inverse function is always reflection of this line in this axis, in this y equals to x line. So when I draw the inverse of this function, so 0, comma 3 was the y-intercept earlier. Now you will notice that 3, comma 0 will become the x-intercept. X-intercept earlier was negative 3 by 2, comma 0. You will notice that it becomes negative 3 by 2, 0, comma negative 3 by 2. So y-intercept become x-intercept. All the x properties switch as y properties. So when I draw the final inverse graph, you will notice that this is how the inverse function look like. So this is, it obviously passes through the point, and so this is the inverse function. So you could just reflect. This is like a mirror line. So this is your mirror. You reflect this part out here and this part out here in order to get the inverse function. So this is a general algorithm to find out the inverse function graphically. So here's one more example where we'll be just kind of working on to see what is the inverse function. So let's say I'm taking a rational function here and x plus 2. 3x minus 2 over x plus 2. And I wanted to find out the inverse of this. Now just remember that the domain for this is x belongs to a real number, x should not be negative 2. And range is y belongs to real number, y should not be 3. That's your horizontal and vertical asymptote. I hope you know how to do that particular part. Now, what we have is, in order to find the inverse of this function, interchange x with y. So it'll be 3y minus 2 over y plus 2. You cross multiply, so it becomes xy plus 2x equals to 3y minus 2. Collect the y terms together and non-y terms one side. So it becomes xy minus 3y equals to negative 2x negative 2. So get y x minus 3 equals to negative 2x negative 2. So what we get is y equals to negative 2x negative 2 over x minus 3. So this is nothing but the inverse function what you got. So this is f inverse x function, which is negative 2x minus negative 2x minus 2 over x minus 3. Or you can say this can be also written as 2x plus 2 over 3 minus x. So that's your inverse function if you just take minus common. Now, if you look at the domain of this as x belongs to real number, x should not be 3, which was exactly the range of the original function. And also, if you look at the domain of this as y belongs to real numbers, and y should not be negative 2. So that's your also the domain of the original function. So this is how you find out the inverse of a rational function. So when you're sketching this graph now,
Sir, 1 second. Sir,
Now, when you're sketching the graph of this, basically what we will have is we're going to have obviously the original graph first. So original graph is something like here. The domain is at x is equals to minus 2. So I'm just going to show approximately x equals to minus 2 line here. X is minus 2, y equals to 3 line. And y-intercept is at negative 1. If I plug x as 0, I get negative 1. And x-intercept is a 2/3. It's 2/3 and negative 1 here. So the graph is going to become something like this. This is the original graph. And here will be you'll have the other part of the graph. Now, when you sketch the inverse of this, obviously you got to reflect this part across y equals to x line. So this is the reflection part. So just to make sure that you reflect this properly. So your graph will be something like, you make sure that you draw these vertical and horizontal asymptotes. So when you draw the vertical asymptote here, what we get is x equals to 3 and y equals to negative 2. So when you draw this here, something like this. Now in this part, the graph is going to be something like this, cutting here like this. And this part comes here, reflection something. So that's how you sketch the graph using the y equals to x line. Now you can find out actually inverse for almost lots of expressions. But now for inverting functions, like inverting function, there's a rule that you need to follow. Now now I'm showing it to you a function which is in a similar line that we did inverse for, which is like, let's say, a simple y equals to x squared graph. Now, when I find out the inverse of this function, like when I try to draw the inverse function for this one, obviously you draw y equals to x line first. So I draw y equals to x line. And now when I invert it, it'll be something like reflection y equals to x line. So it'll be something like this. So this is now here is your inverse function. Now what I look at is very surprising fact is that if I erase this part and I look at the graph now, this function that we call as an inverse is actually not a function because failing the horizontal line test. So what's going wrong out here is that basically not every function will have an inverse for the natural domain. So what is that condition that we can use it? Now, because you can see that this graph is having this inverse, it's not a function. So what we do is, for finding inverse, remember that condition is the must be function must be one-to-one function. One-to-one function. The function must be one-to-one function. Now, what does it mean is that there is something called as HLT, which is horizontal line test. So if your graph is something like this, and if you draw a horizontal line and it cuts the graph at only one point, it means that you can find inverse. you can find inverse for that natural domain. Now, a case like here, which I've drawn here. Okay, so in this case, when you draw a vertical line, a horizontal line, it does not pass the horizontal line test because it cuts at more than a point. Now, in this case, inverse won't exist, but natural domain won't exist. So what do we do in this case? Like if it doesn't exist, we restrict the domain. So what we do is we cut down the part of the graph. So we cut down like one part of the graph, like left of vertex, we retain or we retain the right side of vertex. So in that case, if I have only, let's say, this part, which is here, then the function is one-to-one function. Or if we have something like this, only this part is basically one-to-one function. So just remember that. Now, in a case where like we had y equals to x squared graph, if I retain only this side of the graph, and now I try to sketch the inverse function. Okay, so if I try to sketch the inverse function here, it's something like this. Now, inverse function in this case will be actually a proper function. Okay, you can see that this passes the vertical line test. So this is important consideration whenever you're doing inverse, that for inverse to exist, your function must be one-to-one, or it should be, in a way, it should be increasing like this, or it should be purely decreasing. It can't have like a turn if you are finding inverse. So that's something which is very, very important. So now what we'll do is let us take a simple example of a quadratic where we find the inverse of that quadratic. So let's say I have got x squared plus 4x plus, let's say 4. Y equals to x squared plus 4x plus 4. Now, first question is sketch this quadratic. Now, when I sketch this quadratic, as we know that this is nothing but x plus 2 the whole squared. And if I apply the transformation skill, it is x squared graph, so shifted 2 units to the left. So this cuts at negative 2 here. So this is, firstly, this is a sketch of the graph. And for here, now you can see that the graph is not one-to-one function, not one-to-one function. Okay, so inverse won't exist for the entire part of the graph. Okay, so you might have to restrict the domain of the graph. So how do we restrict the domain? So restricting the domain, they will say, okay, x more than a, inverse exists. Find out the value phase such that it offers the largest domain. Now I can cut down the part of the graph from here onwards also. Like I can just take the part of the graph from here. Still will be one-to-one function. I can take from here. But the largest domain is when I take from here, -2 onwards, and I cut down this part of the graph. So what I do is actually when I'm sketching finding the inverse of this function, I will only consider the right side of the vertex because they have said that. So here the value of a that you get is a value is -2. That's really important point. Now we have to find the inverse of this function. Now how do you find the inverse of this function? So you have got x plus 2 the whole square and interchange x with y. So y plus 2 the whole square. So y plus 2 will be equals to plus minus root x because it's a square function. So this side becomes that way. So y is -2 plus minus root x. Now out of this plus or minus, which one do I choose? Now remember that if you retain the right side of vertex, so if you got like x more than or equals to -2, you take the positive sign. So your inverse function will be 2 plus root x. While if we had taken this side of the graph, then in that case it will be -2 negative root x. So in that case, we'll take minus here out of the plus minus. So in this case, what we have got is we will have to sketch the inverse function. So first you draw the y equals to x line, something like that, and then make the final sketch, which is something like this. This is how you find out the inverse with the restricted domain. So some of the very interesting facts is that the domain becomes a range when you're finding the inverse of a function. It's because your x switches as y. Range become domain. So obviously the vertical asymptote will become horizontal asymptote. The graph is also a reflection y equals to x line. If not one-to-one function, inverse cannot be found. So this is the summary of inverting a function. The process you already got how to do it. So these are the critical points that you got to remember. So now when you want to sketch this graph, firstly, since you see it's a quadratic equation, what you need to do is find out the vertex maybe. So minus b over 2a, if you do this, you get minus 8 of minus over 2 times 2, which is 2. So x coordinate is 2. And to find the y coordinate vertex, you put 2 times 2 squared minus 8 times 2 plus 10. So you get nothing but 2 itself. So the vertex is at 2 comma 2 and the y-intercept is at 10. So it's going to be a quadratic, something like this, which is here. So that's going to be 2 comma 2 at this point. This is 2 and this is 2 and this is 10. So this is the vertex. Now they're saying that is the function one-to-one function. So definitely this doesn't fulfill the horizontal line test. So this is not a one-to-one function. So next up is for expression, find an expression for f inverse for x higher than or equals to a, given that the largest domain, a where a is the a gives the largest domain. So obviously what I do is I restrict the graph only for x more than 2. So means I take only this part of the graph. I cut down the left side of the graph here. So this part of the graph I don't take. Now for this side, I have to find the inverse. Okay, so to find the inverse of this, what we do is we have got the perfect squared form. So 2 times x minus 2 the whole squared plus 2. This is perfect squared form for this. And to find the inverse of this, now you interchange x with y. So it'll be 2y minus 2 the whole squared plus 2. So x minus 2 over 2 is equals to y minus 2 the whole squared. So y minus 2 is plus or minus square root of x minus 2 over 2. Bring to the side. Now, so you get this as an inverse. Now, since you're taking the right side of vertex, you will only take positive. So that's what it is. So now when you find out the inverse of this function, it'll come something like this, reflection in y equals to x line. So coming back to the domain and range. Now when you look at the domain of the original function was x more than or equals to 2, that becomes the range for its inverse, which is y greater than or equals to 2. And a range of the original function was y more than or equals to 2. That becomes domain of the original function, which is domain of its inverse, which is x more than or equals to 2. So this is the general rough explanation for this problem. I have solved this out here as well. So this is something is more clear. So this is what you can see. Over here, I have explained the perfect square form. In case you didn't get how to do this, you can just look at this part. And I have shown the restriction also on calculators. So this part is something that we got, and this is the inverse function. There was an alternative method as well, like which it could be used, which could be used here. So in order to find the inverse of a quadratic, any random quadratic, what you do is you interchange x with y and make y the subject. Now, since you see that there is two y values, it's really difficult. Now, what in this case you do is collect the terms one side and treat it as a quadratic of y, to quadratic in terms of y. And then you can use quadratic formula to solve. So here for me, a value is 2, b is negative 8, and c is 10 minus x. And you could just use the quadratic formula, negative b plus or minus root of b squared minus 4ac over 2a, which is the same as, and eventually get the same answer, which you got through the perfect square. So that's how you do the inverse of a quadratic function. So as far as the perfect square method is concerned, what you can do is this is just an added explanation for it. So what you have to do is just make sure to it that you make the coefficient x squared 1. Now when you do that, you get a quadratic here. Now after this, you see that this is a squared minus 2ab and your b squared is missing. To get the b squared, as you know, this is 2ab term. So if I divide this coefficient 4 by 2, because a is already x, and if I divide this 4 by 2, which is like 4 upon 2, if I do, I get b value, which is nothing but 2 itself. Now when I square that, which is 4, because I need b squared, because I'm adding, I need to subtract as well. So plus 4 minus 4 and plus 5. So this part, what you see here is this is 2 times x minus 2 the whole square plus 1, because minus 4 plus 5 is 1. And you open the bracket, you get this form. So this is how you do the perfect squared form.